Hi, everyone. So let's go over a couple of solutions for the homework set number 2. Um, so you may have seen this problem before if you completed homework 2. If not, that actually is completely normal. The way that the homework sets are generated is essentially the problems are coming from a bank of questions. All the problems are fairly similar, but in any case, it is a good illustration of the type of problem you can solve with the knowledge that you get from chapter 2. Okay, so let's dive in and take a look at this particular problem. So it states that the severity of a fall depends on your speed when you strike the ground. So anytime I read a question like this, I try to pick up the keywords. So here we can see that the speed is going to be very important. And that's the speed when you strike the ground. So we're going to be looking at a fall and essentially how much damage is going to happen depends on how fast you're moving right before you hit the ground. All right, so all factors but the acceleration due to gravity being the same. How many times higher could a safe fall on the moon be than on Earth? All right, so that means that we're looking at that fall, but in two different settings. So we're going to have all conditions be the same. The only thing that's going to be different is that one fall is going to happen on at the surface of the Earth and one at the surface of the moon. Otherwise, everything is the same. So that means that we can take the same object that's falling and everything's going to be happening in the same conditions. Here, I think it's important to state that we talk about the acceleration due to gravity. So that's that little g. We know that's about 9.8 meters per second squared on average at the surface of the Earth. And since we're looking at the acceleration due to gravity, we're going to assume that this is a free fall type of situation. So the acceleration of the object that's falling is going to be given by the acceleration due to gravity. Okay, so we actually know what this little g is on Earth. So we need a little bit more information to figure the rest out because we need more information about the moon, but it's given next. So that is, given that gravitational acceleration on the moon is about 1/6 that of the Earth, if you could jump safely down from 1 meter height on the Earth, from how high a height, it's hard to say in meters, could you jump down from on the moon without risking injury? All right, so again, we're comparing the two situations. Two falls, one on the moon, one on the Earth, and we want to make sure that we're safe. We're told that essentially 1 meter height would be safe on the Earth. What would be the corresponding height on the moon, given that the acceleration due to gravity on the moon is going to be 1/6 that of on the Earth? In other words, the acceleration due to gravity at the surface of the moon is going to be g divided by 6. Okay, so how do we say the answer? You can see that it's given here. You jump from some number times the height without risking injury. So it's going back to the second sentence again. How many times higher could a safe fall on the moon be than on Earth? And we're given a hint. And the first part of the hint tells us to review section 2.5, which is about motion equations for constant acceleration in one dimension. Why is this relevant here? Well, first of all, we're looking at a fall. So that's going to be vertical. That's going to be along a line that's one dimensional. We're looking at constant acceleration. We're assuming a free fall type of situation. Our acceleration is going to be given by the acceleration due to gravity. It's going to remain constant throughout the motion. So we're good to go. So you can go to that section and you're going to be given a set of equations. So we are given in the hint the fact that we should be using the v squared equation. So the hint is given with the equation actually written out in a way that's almost illegible. And I left it like that on purpose, because I know that the first time you see these equations, that's sort of what it looks like. It's very intimidating and it doesn't seem to make a whole lot of sense. So the first thing I wanted to do is actually take a look at this equation and try to decipher and translate, what it's going to do and what kind of information we can get from it. And then we'll see how that can help us answering the question. But before we jump to the equation, I would give, and you can pause the video, but I would try to think just in terms of, conceptually, based on the definition of acceleration, if the acceleration is 1/6 that of the acceleration that we have on Earth, what can we expect for that height? And we know that we have to look at the final speed, like right before we're going to hit the ground. So you can go back to the acceleration of gravity, to the definition of acceleration, which is the rate of change of the velocity. So the fact that our acceleration is going to be 6 times less than what we had on Earth means that our velocity is going to change at a rate that is 6 times less. Meaning that, so first question would be, do we expect that we can jump from a greater height or a smaller height? And so if you think about, if we're going to gain speed at a lesser rate, that means to be able to reach that same velocity that is still safe. So it's going to take more time, it's going to take more distance. All right. So that means that if we think about that in these terms, I mean that we should be able to jump from a greater height because the acceleration is lower. And I'm not going to give you the answer now, but you should try to guess, given the number, so 1/6, what do you expect that height to be? And we can get confirmation. So it's good it helps me personally to look at conceptually, what I would expect, and then mathematically. And in this course, we're going to be doing a lot less of the mathematically. But we can look at these equations and kind of get confirmation of what maybe our gut feeling was telling us. So let's take a closer look at that. Okay, so the equation that we're looking at is the v² equation. So what is it? It's going to give us v². So, and sorry, my pen here is really not working very well. So what does it look like? So I'm going to write it out, and then we're going to go through each term and try to figure out what it means. So we have a v0 squared. Wow, it's really hard to write. It's really difficult to write with this thing. Anyways, I think it got a little bit chewed up by the dog, So, okay. So this is what it should look like, not, what that was. But even written in this way, it may still look confusing. So let's see what all of this is. So I'm going to change colors a little bit here. So what is this? V0 is going to give me a velocity, but it's a special velocity. The not here tell me that we're looking at the time that we start. So it's like t equals to 0. So this is actually the initial. Sorry for the handwriting. It's really difficult to write with this thing right now. So initial velocity. Wow. You can see that we have another one here that's x0, which also relates to the initial conditions, but this is going to give me my initial, wow, I really have a hard time, position. Okay, so initial position, initial velocity. V is going to be my velocity at a later time. So in this case, the later time is going to be right before we hit the ground. So when we're looking at a fall, a lot of the time it's very tempting to look at when the object actually touches the ground, and we're tempted to say, okay, that speed is going to be equal to 0. We stop the motion, but we really want to look at right before we hit the ground. So that's what it's going to be. The corresponding, so X is going to be the position at that exact same time. So it's going to be essentially the object right before it hits the ground, and A is the acceleration. So A is going to be the acceleration of my object. And we know in this case that A is going to correspond to the acceleration to the gravity. So let's put that, so it's still very abstract at this point. So let's draw a picture of what's going on here. Okay, so I'm gonna draw 2 pictures if I can, because apparently, all right, so sorry, this is really bad. Okay, I may have to, go to like paper and pencil for the next video because this is really not working. Okay, so this is supposed to illustrate the ground, and it's not the ground on Earth and on the moon. We're gonna basically assume at this point it's either the Earth or the moon. Why did I draw 2? I have one for initial, and I have one for final. So we're looking at the picture of when we're gonna start the clock and then right before we end the clock. Okay, so when we start initially, so I could draw, if I'm on the Earth, we said it would be 1 meter. So whatever our initial height, and I'm gonna just draw a simple object because I have a hard time writing already. So we're gonna see that we start from this height, and then the final is when we're gonna be right before we actually hit the ground. It should look like the same object at this point if it has not been smashed on the ground yet. So that's going to be my final position. That's going to give me my final velocity. So this is essentially kind of the before and after. Okay, so how do we go from this to using all of these different variables? So initial is going to define my initial position. So this is going to be my initial position. To be able to define my position, I'm going to need to draw an axis to measure all these things. So I'm going to draw my x-axis. I'm going to draw it pointing downward because I know the object is falling. So it's going to make it a little bit easier to track. So again, this is not the best drawing you'll see today, hopefully, but here is where I mark my initial position. And in the same way, I can mark my final position over here. Okay, and you can see that here, what we're looking at is the difference between the two, which is really what we define as the height. That's essentially what we were looking at. So I'm going to call that H to simplify. All right, so we have at this point X, X naught. We have added an extra variable, which is H, but H is going to be defined by what we have over here, okay? Okay, we have those V and V naught. So I can write down over here, initial is V naught. So this is the speed when we start. And we're going to drop our object from rest. So when we start, when you essentially fall, we're going to assume that you're falling from rest. So that means that we can simplify this. This is the best. When you can simplify this and say, okay, my initial speed is equal to 0. That's going to make a 0 in the equation. That's going to simplify things a lot for us. And then our final speed is V, and that's going to be whatever is going to be given by our V squared equation. Okay, one more thing that's actually very crucial here is the acceleration. So if you watch the videos, we know that in free fall, our acceleration should be vertical. It should not be slanted like that. But again, I'm having a lot of trouble with this thing right now. So this is going to be my acceleration, but we know that it's also G. Since my axis is already pointing downward, these two are going to be exactly the same. And there's no negative sign. So I'm just going to say my acceleration is going to be my acceleration due to gravity. Okay, so now if I translate this, I'm going to say, all right, so V squared is going to be equal to 0, my initial velocity is 0, plus 2a, but I say, okay, so 2a is actually 2g, so that's my acceleration due to gravity, and that is the one thing that's going to be changing between the Earth and the Moon. And then times x minus x naught, which was our height. Okay, so that's our equation right here. We can see that there is a relationship between the speed squared, my acceleration due to gravity, and the height. So here, what do we want to look at? So we are going to look at the situation on the Moon and the situation on Earth. Okay, so what are they going to have in common? So we know that the severity of the fall depends on the speed. So we know that the speed before we hit the ground should be the same. So what is that variable? That was our V. So we're going to want the same V for these two situations. Okay, so V is given by my equation right here. Okay, so that means that I need the same thing. So the same 2gh, which is given me my V. We need 2g of moon. I'm going to give that an m for moon times the height that I'm going to have possible on the moon equal to 2 times the acceleration due to gravity. I'm going to put an e for Earth and the height that we had on Earth. Okay, we know one more piece of information at this point. We know that this here, the g of the moon is actually g of the Earth divided by 6. All right, so in order for this, the left-hand side to be equal to the right-hand side, that means that if I'm dividing by 6, I need to multiply by 6 also. So that means that I'm going to have 6 times the height of the Earth, sorry. So I need my height on the moon to be 6 times the height on the Earth for these two sides to be equal. And you can see that if I do that, the sixes are going to cancel out. So that means, and maybe you had the right answer, that you can jump from 6 times the height without risking injury. All right, so I'm going to stop here to keep the video shorter, and then we'll jump to the next problem.